Today, lecture number 3. And in lecture number 3, we are going to discuss about the 3 laws of motion. 3 laws of motion over there. And if I talk about this, around about the time of Greek plague in the 1660s, a chap called Isaac Newton, Isaac, as level AC, Isaac Newton gave 3 laws of motion over there, and he worked for 3 laws, where he explained about the force relationship and motion and the relationship between them. And if we go for these laws, then I will say here, first law is states about first law states about the balanced forces, mean no change in velocity. He talked about balanced forces when there was no change in velocity. Change in velocity over there. If I talk about this, I will simply say here, if we say that so long as the force on an object are balanced, then it will stay still, and already moving, it will just carry on the same velocity if it is moving. If it is already moving, then it is continuous state, and overall, as long as all the forces are balanced over there, then I can say a body continues its state of rest or motion, its state of rest or motion until no external force acts on it. Until no external force acts on it. Then it is called first law, Newton's first law of motion. This is also called law of inertia. And inertia is a property of a body. Inertia is property of a body which resists any change in its state of rest or motion over there. So I can talk about this when, for example, when a train or car or bus or anything else is moving at constant velocity, then the forces on it must be imbalanced. Or I will also say, never let yourself to entertain the ridiculous ideas that things need to be constant overall forces to keep the moving. Never and no over there, okay? And to keep going at a steady speed, there must be zero resultant force. And don't you forget it about this. Whenever you are saying that he is going to steady speed, then there must be zero resultant force. Means I can say summation of all the forces equals to zero. Don't go that engine is still on and it is making to confuse over there. Now I will move towards Newton's second law of motion. And here I will also tell you inertia is a property of body due to which it resists any change state of rest or motion. And inertia depends upon mass of the body over there. Let's move to Newton's second law over there. Newton's second law or second law of motion over there. Second law. It states that, for example, you are taking, there is a body of mass m and you apply a force F on a body and an acceleration in the direction of this force is produced on that body, then we can simply say here that uh, overall unbalanced force is produced, which is accelerating force for this body over there. And unbalanced force always produces acceleration or deceleration over there. Here I can say unbalanced force always produces acceleration or deceleration over there, which is we can say which is responsible for increasing speed or decreasing speed with which it was going on in the previous state over there. And acceleration can take 5 different forms. For example, acceleration here I am also mentioning over here, acceleration can take place in following forms or following conditions over there. In that case, I will say here, for example, you are starting your travel with some speed. It means you are increasing, means when you are starting the travel over there, then the acceleration is present. At number 2, I will say when you are stopping the vehicle over there, acceleration will be produced by the application of the force over there. It can be when you are going for speeding up. For number 3, I will say for speeding up, you will get acceleration to be produced in that body over there. At number 4, I will say here when you are slowing down. And in the last, for number 5, I will say here that when you are changing the direction of motion and direction, then it means acceleration is produced in that body over there. And here I will also mention that, for example, you are taking a body over there. Don't ever say if something is moving, there must be an overall resultant force acting on it, because net force can be zero. Not so, if there is overall force, it will always accelerate and you get steady speed from the balanced forces. And I wonder how many times I need to say that same thing before you remember it. So try to understand and don't make ridiculous thinkings over there. After that, I will simply say here, as I am going to explain this relation now, the acceleration produced in the all 5 scenarios over there, that produced acceleration is directly proportional to applied force, and this acceleration is inversely proportional to mass of that body. If I combine both of these relations over there, then I say A is directly proportional to F over M over there. And if I remove this proportional sign and I introduce a constant over there, then it is Kf over M in that case. So if I take force as 1 Newton, as a condition to remove this constant as a value of 1 over there, acceleration as 1 meter per second square, and mass of the body as 1 kg, then I will say I will have to take this k to get the value 1. So A is equal to F over M, which can also be written as F is equal to MA. So I will say here that this unbalanced force or resultant force, if I give a word equation for this formula, I will say resultant force is equal to mass into acceleration over there. So this is the way how to move towards the main scenario of this. And if I am going to explain according to the relation that how acceleration is showing the force relationship over there, then I can say if acceleration is high, it means force is high and mass is smaller in that case. And if acceleration is high, mass should be smaller. If acceleration is high, force should high. So the relationship according to this acceleration directly and inversely can be explained on the basis of that. And to get a big mass to accelerate as fast as small mass, it needs a bigger force according to this relation we can say here. So remember this formula, F is equal to ma, and you can make the triangle for memorizing this. F is equal to m a over there, and use this relation when you are taking this, when you are going to find mass, take it force over acceleration. If you want to go for acceleration, then go for force over mass. Then it will be calculated by using the formulas. If I mention here, A is acceleration having unit meter per second square, mass is having the unit kilogram, then force will have unit that will be named as kilogram meter per second square. Also, with the name of Sir Isaac Newton, it is also be written as Newton over there in many cases. So when we go towards the third law, Newton's third law of motion over there, you can say that a resultant of the forces, if before going towards Newton's third law, I will give some examples about it, that the notation of resultant force is really important for you to get your head around. It is not especially tricky. It is just seems to get kind of ignored like that. So in most real situations, there are at least two forms acting on the object along any direction. Overall effect of the forces decide the motion of object, whether it will accelerate or decelerate or stay steady speed. So always remember, if there is an object which is moving in forward direction and backward frictional force is present, then their net force is going to decide that whether it is going with acceleration or it is going with the deceleration or it is going with steady speed over there. Acceleration or with the steady speed over there. So this is the case how to accelerate or decelerate an object. If the force along the same line, then overall effect is found by adding or subtracting. Like for example, I'm here saving here that 7 Newton on right side and 4 Newton on left side. Then you are saying net force is 7 minus 4, you are getting 3 Newton. But if it is not exactly on the same line, like left, right, like that, and you are getting some inclined angle over there, then you must have to take to go with the formula section of resolving that force into its vertical and horizontal components over there. Okay, let's move towards Newton's third law, which states like that by saying Newton's third law of motion, which states that every action has its reaction equal in magnitude but opposite in direction over there. So when I define this, I will say here that let's suppose there is a body A and there is a body B, or object F, object A is exerting a force on object B, exerts a force on object B. Then we can say here, then object B will also exert the same force, exerts an equal and opposite force on object A, equal and opposite force on object A over there. And in that case, I will say every action and reaction have equal magnitude but opposite direction. Every action and reaction acting on different bodies acting on different bodies are equal in magnitude but opposite in direction. In direction over there. So whenever you are going to observe Newton's third law, always remember that you will have to go for different scenarios to be provided for Newton's third law of motion over there. Okay, if I go to explain this more, it means that if you push something, say like a shopping trolley over there, trolley will push you back against you just as hard like that as you are pushing it. And as soon as you stop pushing, so does the trolley kind of clever really like that over there? It will also stop over there. So for so good, the straight tricky things to get your hand around is this. If the forces are always equal, how does anything overgo anywhere? So the important thing to remember is that the two forces are acting on different objects. Think about a pair of ice scatters over there. When a scatter, like he is skating on ice over there, when scatter A pushes on scatter B, the action, and she feels equal and opposite force on scatter B as a reaction force. So both scatters feel same sized force in opposite directions. So we can say they accelerate away from each other, and scatter A will be accelerated more than accelerator B because she can be having a smaller mass. And remember that that is force is equal to ma. And it is the same sort of thing when you go swimming, when you push water back and water pushes you forward. So these were little bit examples related to Newton's laws of motion over there. If I am going towards combining forces over there after three laws of motion, then I will have to go for vectors addition over there to work out. Then I will say when there are multiple forces, like I am going to title here, combining forces. How I am going to do the combining of forces over here, then I will say when there are multiple forces on an object, it is often useful to know the resultant force acting on the object. For example, I am saying there is an object which is two forces. One force is acting in this direction, one force is acting in this direction. And you are saying your engine of this small car is exerting 800 Newton force, and it is accelerating, decelerating because of the friction over there. Some force is lost. That is, I say, that is 600 Newton. And you want to know how much the total net force is acting on this object over there. Then to do this, you will have to need the size of different forces acting on the object and their direction. You should must know. If I say 200 in the same, this Newton is in the same direction is going to apply. It is having the 500 Newtons over there. So what is the net force and where the body is going on? As we know, force is a vector quantity. It has its proper direction with its magnitude. Lots of physical quantities are vector quantities over there. Then I will say here that net force by combining these, for example, it is 600 plus 500 in the left direction should be subtracted with 800 plus 200 over there. So it is 1100 minus 1000, and I am getting 100 Newton as a combined net force. As I stated here, force is a vector quantity. Then we can say, so if we talk now about next section over there, as I told you that force is a vector quantity, and if I want to explain a little bit about the vector and scalar quantities over there, then I will say here the vector quantities are those quantities which have magnitude plus direction plus unit over there. And if I give the example for vector quantities, then I will say velocity, acceleration, force, moment, momentum. So these are the little bit examples which are related to vector quantities over there. And if I go for scalar quantities, they don't have any specified direction over there. Means they have their magnitude and unit only. Magnitude and unit only. And for example, work, for example, speed, I will add the displacement also in the vector quantity. Displacement. And here speed, distance, after that power, after that density, after that pressure. All of these are scalar quantities over there. Okay. So I can say here to work out the resultant force, you need to combine the vectors over there, and you will have to get the resultant as the difference or as the sum. If they have same direction, if force vectors have same direction, then they will be added. Otherwise, they will be subtracted. They will be subtracted. Here I am not involving the inclined form or something else to be going in more detail. That will be discussed in A levels like that. So not to worry about that phenomenon over there. Here I am also adding about terminal velocity over there. Terminal velocity. Terminal velocity is where if I simply say here, there is an object which is falling downward with a constant velocity when drag force of the air and weight becomes equal. Like drag force, weight is acting downward and drag force is acting upward. When both weight and drag force are upthrust acting due to air on this object to fall down becomes equal, then velocity becomes constant. Such velocity is called terminal velocity over there. And if we say that frictional forces increases with speed, as in the previous lecture, I told you that, for example, you are going with the 30 km/h speed over there, then you take your hand out of your car. It is easy to face that. But if you are going with 200 km/h over there, then it means it is very difficult for you to understand related to that phenomenon over there. And but when I am talking about the resistive force in case of drag force over here, then I say as you start, your drag force is low. As you are going on to move like this point, if I am adding there, this is the point where both gets equal over there. And it reduces the acceleration until eventually the resistance force is equal to the accelerating force. And at the point, the object would not be able to accelerate anymore because it is coming with a constant velocity over there. That velocity is called terminal velocity over there. And this terminal velocity of the objects depend upon the factors of their shape and their surface area, which is going to take part in man phenomena. So the accelerating force acting on all falling objects is gravity, and it would make them all accelerate at the same rate. So it was, if it was not for the air resistance over there, to prove this on the moon where there is no air like that, and hamster and feathers are dropping simultaneously, and we can say they hit the ground together. So in that case, I can say, however, on Earth, air resistance causes to fall different objects at different speeds over there, and the terminal velocity of an object is determined by the drag force compared by its weight over there. So just keep it in mind over there. So drag force depends on shape and area of the object over there. And the most important example is the human skydiver. For example, you are diving with the help of your parachute over there. And when you are saying that your parachute is not open and you are facing with your weight and only with your means you are facing with weight and a small surface area of your body as a drag force over there, and you are coming at very fast terminal velocity at that case. And when means I can say without parachute open, you will have a quite small area and force equal to weight pulling him down over there. So he reaches a terminal velocity of like round about, I can say, 120 mile per hour like that. But when parachute is going to open, then I will say here in that case, there will be much more air resistance and still the force is pulling down. This means the terminal velocity comes right down to about like 15 mile per hour. With parachute, it is 15 mile per hour. It means you can easily land over there. But if you are not using parachute, it is round about 120 mile per hour, which is very much high and it can hurt you. In both cases, once the skydiver has reached the terminal velocity, the resistance is equal to the weight. So always keep this in mind when you are discussing about terminal velocity case of the scenario over there. And the difference is the speed at which it that happens is because of the surface area and shape of that body over there. Okay, in tomorrow class, we will go towards the Hooke's law over there and we will discuss that. Thank you so much for today, and revise Newton's laws and their implementations according to different types of forces. Thank you so much.